Well, here we go. We're moving into Unit 4, which focuses on cation exchange capacity and base saturation within soils. There's 6 learning objectives that you need to know for this unit. Number 1, you should be able to define cation exchange capacity. Learning objective number 2, understand basic clay mineralogy and specifically isomorphic substitution as a source of cation exchange capacity. Really important, point number 2, to understand this. Objective number 3, understand the relative difference in cation exchange capacity among 1-to-1 and 2-to-1 type clays, as well as organic matter, and be able to explain how pH affects cation exchange capacity. Point number 4 for the objectives, understand the meaning of equivalence as a unit of charge density and be able to calculate equivalent weight of cations. We touched on this a little bit in Unit 3. We'll touch on it again here in Unit 4. Objective number 5, calculate cation exchange capacity and base saturation. You should be able to do this. And point number 6 is memorization. Memorize and understand the lyotropic series and how it affects cation exchange reactions. So with that said, let's get into Unit 4. Cation exchange capacity. What is cation exchange capacity? You probably learned about this in an introductory soil science course. And it can be defined a number of different ways. We'll try to keep it simple for this class. It's simply the quantity of positive charges, or cations, that a soil can hold. And these are the cations that are, quote, stuck on the soil and remain able to exchange with cations found in the soil solution. And what I mean by stuck on the soil, they're actually adhered to exchange sites on clay particles or minerals, as well as potentially negative sites on organic matter. And so, where does this cation exchange capacity come from? It's not magic. It's really not magic. And we've known where cation exchange capacity comes from for almost 100 years. So, when you look at soil particles, or the soil separates specifically, sands, silts, and clays, where does CEC come from? Sand-sized particles are rather large. Silt-sized particles actually look like sand, just smaller. And clay-sized particles have a lot of surface area. All right, so we've talked about surface area a few times so far in this class. And surface area, or a large amount of surface area, equals great reactivity in soils. And so you can just imagine the surface area of kaolinite, which is a 1-to-1 type clay. We'll talk about what that means in this unit. But these are plate-like structures that stack upon themselves that have a lot of surface area. And then you have 2-to-1 type clays like this illite smectite over here that looks like an amorphous blob. And it has a greater surface area than kaolinite. And it is structured, believe it or not, but the surface area is greater and there's greater reactivity in these types of clays, which are 2-to-1 types of clays, than these types of clays, which are 1-to-1. The reactivity, or cation exchange capacity, comes primarily from the types of clays that are present in soils and organic matter, and maybe a little bit from silts and sands, but CEC is dominated by the types of clays and organic matter present. So with that said, the building blocks for clay minerals are comprised of 2 different types of structures. And I hope you remember some of this from your introductory soil science course. The first type of structure is called the silica tetrahedron. And the silica tetrahedron is 4-sided. It has 3 oxygens sort of on the bottom and 1 on the top. And in the center is silicon. and it fits perfectly within these 4 oxygens. And there's 4 sides to it. I don't know if you can see that, but there's a plane on the bottom, there's a plane on this side, there's a plane facing you, and there's a plane facing away from you on the back right. So this is one of the basic building blocks for clay minerals. These silica tetrahedron building blocks come together to form sheets that we call tetrahedral sheets, right? And so you can imagine a big plane of these sheets, and that's one tetrahedral sheet, okay? This is one of the building blocks of clay minerals. The other building block of clay minerals is called the aluminum octahedron. And the aluminum octahedron has 8 sides to it. And we call it an aluminum octahedron because aluminum is in the center. So it's a little difficult to see, but it is 8-sided. There's a plane in this direction. There's a plane on the bottom, and then there's a plane over here. There's a plane here. There's a plane facing away from you. There's a plane in the back. There's actually probably 2 planes in the back. And it sort of looks like a dreidel, if you've ever seen a dreidel. The aluminum octahedrons come together, just like the tetrahedrons, to form sheets. The complexity is certainly more complex than the tetrahedral sheet. When the tetrahedral sheets are formed, or the octahedral sheets are formed, there's sharing of oxygens between the tetrahedrals or the tetrahedrons that comprise the sheets. So there's sharing of oxygens, and the same thing occurs in the octahedral sheets. And I can tell you that when the sheets are created, the overall charge of either the tetrahedral sheet or the octahedral sheet is 0. There's no charge on this, okay? But charge does form in these sheets, and I'm leading you to that point. So, what is meant by 1-to-1 type clays? These are aluminosilicate clays. The silica tetrahedral sheets and the aluminum octahedral sheets join together to form a 1-to-1 type clay. And what we mean by that is there's 1 tetrahedral sheet to 1 octahedral sheet. And you can see it in this cartoon. Okay, so that the tetrahedral sheet is down here, and the oxygens are shared with the octahedral sheet, right? And this pattern repeats itself. They stack on top of one another. Now, the picture that I showed you of the kaolinite earlier showed stacking, and it typically, when you see the stacking in an image like I shared with you before, the stacking is comprised of likely 100 of these repetitive sheets stacked on top of one another. You can't see the individual atoms. So let me show you a picture. So here's a picture of, or a cartoon of a 1-to-1 type clay, right? This is likely kaolinite. That's the name of the clay. You can see the tetrahedral sheet and octahedral sheet looks a little more complex, but the tetrahedral you can pick out. So it's 1 sheet of tetrahedrals or tetrahedral sheet and 1 octahedral sheet. And then it repeats itself, a tetrahedral sheet, an octahedral sheet, a tetrahedral sheet, an octahedral sheet. These stack up on top of one another to form the stacks that you see in this scanning electron microscope image. These are 1-to-1 type clays because it's 1 tetrahedral sheet to 1 octahedral sheet. There are other type of clays, though, that are present in soils. And to keep this explanation simple for this class, we'll just focus on 2-to-1 type clays. These are aluminosilicate clays that are 2-to-1. That means that there's a silica tetrahedral sheet and an aluminum octahedral sheet that come together to form this structure. And when we say 2 to 1, we mean that there are two tetrahedral sheets that come together in conjunction with one aluminum octahedral sheet to create the layer of that clay. So you can see it in this cartoon. The very bottom layer here is a silica tetrahedral sheet. You can see the structure. And at the very top is the same or similar silica tetrahedral sheet. And sandwiched in between is an aluminum octahedral sheet. And they're sharing of oxygens. Now, these also stack up on top of one another to form the clay. So let me show you a picture. So here's a picture of a 2 to 1 type clay. And if we look at the structure at the bottom, this is the tetrahedral sheet and another tetrahedral sheet on the top, and then a more complex looking aluminum octahedral sheet sandwiched in between. And this structure repeats itself and repeats itself and repeats itself until you have a stack of maybe about 100 of them where you can actually see their structure. And so in these two pictures, here's kaolinite on the right-hand side. I always think of kaolinite as, I don't know if you've ever, when you were younger, had the ice cream man come down your street. When I was younger, the ice cream man came down my street and you gave him some money and he gave you change out of this machine on his hip that went ching, 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 and it had quarters that were stacked up on top of one another. This is what the kaolinite looks like to me. It looks like the quarters that are stacked up in the ice cream man's coin dispenser. Smectite, which is a 2 to 1 type clay, looks nothing like kaolinite. And the ice cream man certainly didn't have this in his dispenser. If you look at smectite a little bit closer, there is structure to it. And each one of these planes that you see is likely somewhere between maybe 80 and 100 of these sheets or structures stacked on top of one another. That's what you see here. So this 1 to 1 or 2 to 1 type clay structures, or more specifically, the tetrahedral sheets and the octahedral sheets that come together to form 1 to 1 or 2 to 1 type clays, are the building blocks of the clays that we have in our soils, not only in Ohio, but worldwide. Next, we'll talk about how clays become negatively charged.